이번 시간에는 챕터 5, 챕터 1을 지난 시간에 했었는데요. 챕터 5는, 챕터 2, 3, 4는 사실 뭐 그닥 중요한 내용이라고 생각 들지가 않아서 생략을 하도록 하고요. 챕터 5는 Signals and Noise라고 되어 있습니다. 그래서 우리가 여러 가지 이제 분석 방법에 대해서 배운다고 말씀을 드렸는데, 분석 방법을 뒤에서 다시 보여드리겠지만, 예를 들면은 이런 식으로 뭔가 분석 방법, 어떤 실험 방법을 통해서 뭔가 측정을 하게 됩니다. 측정을 하게 되면 이런 식의 어떤 시그널, 어떤 우리 신호라고 하죠. 우리가 원하는 어떤 정보, 우리가 측정하고자 하는, 우리가 알아내고자 하는 어떤 물질이 갖고 있는 그런 정보를 담고 있는 우리가 시그널을 측정하게 되지만, 또한 시그널 말고 우리가 원하지 않는 정보들, 예를 들면 막 이렇게 자잘하게 이렇게 조그마한 이런 변화들, 마찬가지로 위에 A볼을 보시면은 굉장히 그게 심하죠. 이런 우리가 원하지 않는 정보를 우리가 노이즈라고 합니다. 그래서 그러면 도대체 시그널과 이 노이즈라는 게 방금 전에 뭐 간단한 정의는 말씀드렸지만 도대체 무엇이며, 그럼 도대체 우리가 원하는 정보만 어떻게 하면 더 많이 얻을 수 있을지, 당연히 우리가 이제 그걸 극대화하기 위해서는 우리가 시그널 투 노이즈 레이쇼라고 해서 노이즈 대비 시그널이 얼마나 큰가 라는 점을 이제 주로 우리가 비교를 하는데요. 당연히 이제 이게 크기만 클수록 좋은데, 그렇게 하려면은 시그널을 키우던지 아니면 그만큼 마찬가지로 노이즈를 작게 만들면은 당연히 요거를 크게 만들 수가 있는데, 어떻게 하면 우리가 이걸 할 수 있는지 여러 가지 방법들, 어떻게 하면은 이 시그널 투 노이즈라는 그 레이쇼를 증가시킬 수 있을지, 어떻게 하면 인핸스 할 수 있을지 여러 가지 방법들에 대해서 배울 것이고, 이거를 알려면은 어떻게 하면 노이즈를 줄일 수 있을지, 다시 말해서 어떤 종류의 노이즈들이 존재하는지, 왜 그런 노이즈들이 생기는지 그 이유를 우리가 알 필요가 있겠죠. 그래서 이러한 것들을 챕터 5에서 다루도록 하겠습니다. Okay, so in chapter 5, as I just mentioned, we'll learn about signals and noise. Signal is the information on analyte that we have interest in, and noise is unwanted information, and it could be generated by thermodynamics or quantum effect, etc. So we'll learn about how to enhance signal to noise ratio and what types of noises are present, their origin, and also the ways how to enhance signal to noise ratio. Okay. So, as I just explained, the signal is defined as what you are measuring that is the result of the presence of your analyte. So basically, signal is something that analyte gives us, that useful information. Okay? And noise, on the other hand, is extraneous information that can interfere with or alter the signal. So this is information that we do not want, right? Noise is something that we have to avoid, right? But the problem is noise cannot be completely eliminated, but hopefully reduced if we know how noise are generated and also what types of noises are present. Okay? Then if you know the mechanism of noise generation, then we can try to reduce the noise level. Okay? And the important information about noise is that noise is considered random. You remember from previous class in chapter 1, there was random error, right? So that was represented as such as standard deviation, right? That cannot be avoided, right? So basically there always are noises, okay? And the average strength of the noise is relatively constant, does not change as a function of time or as a function of measurement. So, if you increase the number of measurement, that usually decrease the noise level. So we'll get back to that point again later. Okay? Alright. So we already saw this figure, right? You can simply say that spectra A has much more noise than spectra B, right? It shows very clear signal that we want to get, right? From the analyte that we want. Okay? although we did not really learn about the signal to noise ratio, S over N, we can just simply just check the number. For this spectra A, SN ratio is 4.3. On the other hand, for spectra B, SN ratio is 43, much larger, right? So you can clearly see the difference between high noise and low noise spectra. Alright. Okay, let's first consider signal. In all experiments, there is response from the sample, from the analyte. Okay? But also, there is a response from blank sample, even if there is no analyte. Okay? So, the signal, definition of signal, is the difference between the sample and blank response. Okay? Let's say that the output signal of the blank sample is here, and when there is a sample, when there is an analyte that we want to measure, the output is here. Then the difference between these two lines, these two levels, is defined as signal, right? It's very simple, right? This response of blank sample, blank response, would be ideally zero. Ideally, in ideal case. But the problem is it is not zero in all cases. This is never the case, though it can often be adjusted to be close to zero. Okay. So, this blank signal, the signal which is measured for blank sample, is called baseline or background. Okay? So there is always baseline or background for all samples. Blank sample for just the analyte. Okay? But the difference between sample and blank signal is same, right? As signal, as we defined signal in previous slide, right? Because baseline or background is always present for all samples, even for blank for sample. Okay. This baseline, the signal of background, is constant in time ideally. Okay. Then it will be very easy to calculate signal. You can simply subtract signal, the blank signal from sample signal. But the problem is, sometimes, in most cases, baseline changes slowly with time, such as like this. As time goes by, baseline increases, right? Okay. If this change, which is called drift, this change of baseline is linear in time, then it'll be very easy to calculate the signal, right? Okay. But the problem is sometimes it is more complex and difficult to predict. Sometimes baseline increases, decreases, and something like that. Okay. That makes the measurement very complicated. Okay. All right. This is the basic properties of a signal. Okay. How about noise? The definition of noise is as follows. Noise is a random or almost random time-dependent change in the instrument's output signal that is unrelated to the analyte. Okay? So because of noise, that makes the accurate measurement less certain. It makes accurate measurement difficult. Okay. This is the definition of noise. And noise arises from many sources. There are many different types of noises, and we'll discuss them later. Okay. The frequency response can span the entire spectrum. Noise changes as time, right? It could increase, decrease, etc. continuously. So we generally treat noise as if it were a sine wave, just like this. Increase, decrease, something like that. Because noise changes as time continuously. Okay? So we'll treat noise as sine wave, and we'll from that assumption, we'll treat noise and also signal to noise ratio, etc. Okay. So, as I mentioned, we'll treat noise as this kind of sine wave. Increase, decrease continuously. Okay? So how can we define noise? There could be many different ways to define noise. Okay? The first way is just check peak-to-peak noise. Basically, the difference between highest peak and lowest peak. This difference. Okay? So one measure of amplitude of a sine wave is the peak-to-peak amplitude, just this distance. Okay? Sometimes we use this peak-to-peak distance to define noise, but that's not the general case. If noise is, this is much more like common noise type, which is not really sine wave, but we can roughly consider this noise as collection of sine waves. Okay, so that's not. We can simply assume that the noise has sine wave form. Okay. So how can you mathematically define noise? How about averaging noise? Since noise changes continuously as a function of time, how about just simply average it? Okay. The problem is, if noise is truly random, increase, decrease, something like that, the problem is, if we average them, it should equal to 0, right? As you saw here, if noise is assumed to be a form of sine wave, positive, negative, positive, negative. If you average all of this noise as a function of time, then it should be equal to 0, right? Okay. So the problem of use noise as average value is not useful. Okay, since it is just 0, right? We should have another way to define mathematically the noise level. Okay, easiest way is simply take the root mean square. Okay. Since noise have positive and negative value, we simply take the square of this number. Okay. By taking root mean square of each point of each value of noise, we can have positive numbers always, right? Okay. Because we take square even with minus numbers of noise. Okay. So if we have perfect sine wave, and if you take the root mean square value, we get this value. Root mean square noise value is given as 1/2 root 2 times noise peak to peak value. Okay, it's about like 0.35. Let's see why we have this number. Okay, all right. Let's go back to the whiteboard. Okay. All right. So basically we assumed that noise is sine wave as a function of time, something like that. Okay, you can see it, right? We assumed noise is sine wave, and let's assume that its amplitude is A. Then root mean square noise can be defined as root, because it's root mean square, of average of all the values as a function of time. If you average it from 0 to time t, all the square values of noise should be calculated from 0 to t and t square dt, right? So this is nt, basically this function, noise function as a function of time, and t, since we assume that noise is sine wave, should be something like this: a sine omega t. Here omega is t over 2 pi over t. Okay, t is time, okay, period. Okay. So if you calculate this, let's calculate n root mean square. You can just remove root. Then what we get, you put this here. What you get is 1 over t times a square integral 0 to t sine omega t square dt, right? Very simple, right? Not let's use small t here. Okay. So if you calculate this, you basically get a square over 2. Okay. So root mean square noise level is root 2 over a, which is same as 2 root 2 2a. 2a is equal to n peak to p. Okay, so that's why noise level, the root mean square noise, is defined as shown in this slide. Okay, please check this whiteboard. Okay, so we usually use this number, root mean square noise, as noise to calculate signal to noise level. Okay, so let's take an example. How can we calculate signal to noise ratio? Sorry, there is a misspell. I'm sorry. Here. Okay, something like this. Okay. Let's say that we have this kind of graph, and we want to calculate signal to noise ratio. To calculate signal to noise ratio, we need to check the value of signal and check the value of noise. Okay, and noise can be calculated as root mean square value. Okay, all right. So signal, the difference between output of analyte and baseline is given as 0.75. Okay, and noise peak to peak value is given here as 0.01. Okay, 0.10. Okay, then we need to calculate noise root mean square value, right? Noise root mean square value was defined as 0.35 or 1 over 2 root 2, okay, times peak to peak noise value 0.1, then it is 0.035, right? So signal to noise ratio can easily be calculated by dividing 0.75 the signal by root mean square noise value. So signal to noise ratio is 21.4 in this graph. Very simple, right? All right. So to enhance signal to noise ratio, we need to reduce as much of the noise as possible by carefully controlling condition. We can control various conditions such as temperature, power supply variation, etc., etc. Okay. And if we increase signal to noise ratio, which means that we basically have lower standard deviation, lower noise level, then if noise level is small, then we could have better limit of detection. So it makes that specific instrument or specific analytical method much better. Okay? And signal to noise ratio of 3 is usually the minimum that can be acceptable. SM ratio would be better if it is really high, but at least it should be at least more than 3. Okay? So now let's move on to the kinds of noise. So overall, there are 2 different kinds of noise. First, chemical noise, and second, instrumental noise. So chemical noise are generated by undesired chemical reactions or environment, such as temperature variation, pressure variation, or humidity variation, etc. Okay? So they are reaction or technique or instrument specific. Okay? Right? So if you control this environment, basically, if you control the temperature, pressure, or humidity constant, that can reduce or possibly remove chemical noise. Okay? That's not really a big deal. On the other hand, instrumental noise is a big problem. It affects all kinds of instruments, and it can often be controlled physically or electronically. Okay? There are several ways to control, to reduce instrumental noise. Overall, there are 4 or more different kinds of instrumental noise, which are thermal noise, shot noise, flicker noise, and interference, or environmental noise. So let's go into the details of these specific kind of instrumental noise. Okay, the first one, thermal noise. Thermal noise is originated by basically thermal agitation of molecules. All molecules, all electronics have thermal movement of charged particles, such as electron. Because of those thermal agitation, there are voltage fluctuation. The voltage changes as a function of time. That is the origin of thermal noise. Okay, so thermal noise arises because the atoms of a solid
state conductor are vibrating at all temperature and they bump into conductors, etc. Something like that. Okay. So thermal noise is given as this kind of equation. As you see, it is proportional to root of T, temperature, R, resistance, and B, bandwidth. So if you decrease temperature or decrease resistance or decrease bandwidth, we can possibly reduce thermal noise. Okay. Next type of noise is called Schottky noise, also known as quantum noise or Schottky noise. It arises wherever charged particles or electrons cross the junction. Okay. Schottky noise arises because charge and energy are quantized. I believe that most of you have taken quantum chemistry class, or even in general chemistry class, there's quantum chemistry, right? All energies, all materials are quantized, right? Because of this quantum effect, there is Schottky noise. Okay. And Schottky noise is given as something like this. The details are not that important, so we only need to understand the basic mechanism, why different kinds of instrumental noise are present. Okay. Third type is flicker noise, also known as 1/F noise. Origins are uncertain, depends on material design, nature of context. So basically, it is proportional to 1/frequency. Okay. So if you use high frequency, then we can possibly reduce flicker noise. The fourth type of instrumental noise is interference, or known as environmental noise. All the instruments have conductor, such as metal, right, inside of the instrument, and all the conductors can potentially behave as antenna, right? Antenna which can pick up electromagnetic radiation. It can pick up any type of electric signal from the air, right? So if you look at this spectrum, noise spectrum, this is noise spectrum in normal university lab. Okay. So there is noise as a function of time because of temperature, change of classes, elevator is also conductor, right? Also from radio, TV signal outside of the environment, right? All these things can be picked up by instrument. So that's the origin of interference or environmental noise. So to reduce this noise, this instrumental noise, we have to use either physical or electronic ways. Okay. First method to reduce noise is hardware device, to use of hardware device. We can ground or shield the instrument to protect it from outside electromagnetic radiation. Okay. Or we can use different types of instrumental amplifiers. Okay. Or we can use analog filtering. So by using some kind of analog filter, we can reduce noise from like high frequency range or either high frequency or low frequency range. Okay. Modulation is something that something about the flicker noise. As you remember, flicker noise is 1/F noise, which depends on frequency. Okay, so if you use high frequency range, then they can possibly reduce flicker noise. There's also software method to reduce noise level. So there are several types of software method. So basically we use software or computer program to reduce noise. Okay? The easiest way is simply averaging. We just measure same signal again and again, many times, and we average it. Then that can reduce the noise level. Okay? Let's see an example here. Okay. So, before we take the ensemble average, each spectrum looks like this. First spectra, second spectra, third spectra, which all of these are a little bit different, right? First, second, third, and fourth spectra. And we just simply average it. We just add it up and divide it by 4. And we get something like this. Look much better than each of these 4 spectra, right? Okay. I already mentioned about this in the earlier section of the class. The reason why this ensemble average increases the SN ratio is that let's say that we measure multiple times. For example, like n times. We take n measurement. A signal is basically proportional to number of measurement, n. And noise, which was defined as usually as root mean square, right? So it is proportional to root n. So S over n, SN ratio is proportional to root n. So if you increase n, if you take more measurement, that increases basically SN ratio. That makes things better, right? That's why ensemble average works. Okay. Okay, let's see another example. All right. Sorry. Oops. Okay. Okay. Another example. This is the first scan. And we take multiple scans and we do the ensemble averaging. After we add 50 scans, it looks much better, right? After 200 scans, even better. So if you take more and more measurement, that increases SN ratio. Okay. There are also other types of averaging method. Boxcar averaging. It takes an average of 2 or more signals in some domain. So basically, it averages small number of adjacent points. So let's see an example. Let's see a figure here, like this. Okay, this is the original signal, and what we do is we take the average of these 3 values, 1, 2, 3, as here, and these 3 as here, something like that. We just take the average value of adjacent signals, and the resulting signal looks a bit better, a bit higher SN ratio, right? Okay. But the problem is boxcar averaging is only useful for data where only the average amplitude is important. Okay? So you lose some detail in the overall signal, as you see here, right? So you lose some detail here, right? It looks like this, right? It became smooth, but not really detailed, right? Another way is software low-pass filtering. So basically what you do is filter some portion of signal, some noise portion. So if you take the low-pass filtering for this signal, you can have something like this. The details is not that important. Okay. or there are other different types of averaging way, right? We can put some weighting factor, right, at each point, and it gives some different numbers, something like this. Okay. We can also do differentiation by choosing the right integer, and we can have a bit more details. The next smoothing way is called Fourier smoothing. I believe that you guys all learned about Fourier transform in the mathematics class, right? That's this one. Okay. So Fourier transform basically decompose a spectrum into many sinusoidal contributions that make it up. Okay. Since noise is generally high frequency, drift is low frequency, a Fourier spectrum, selective removal of offending frequency components followed by an inverse Fourier transform. So basically, during this Fourier transform, we change time domain into frequency domain, and we remove some frequency part to remove noise, and then we go back to the time domain. Let's see an example. Okay. So this is the original spectra as a function of time, t. Okay? Mathematically, we change this to frequency domain as a function of frequency. Okay? Then what we do is we remove some part, right? For example, like we multiply this with this. So below this frequency, we just maintain the data, but above this, we just take it as 0, right? We simply remove this. If we multiply these two, we get this, right? Only this part remains, and we mathematically do the inverse Fourier transform, then we get this. We removed basically high frequency noise from the original data, right? Okay. So this kind of Fourier transform is performed in many modern instruments, and they just do it automatically by using computer program. You do not need to do it manually. Okay. Okay. So that's pretty much it. Okay. So this is the end of chapter 5 about signals and noise.